So let's have a look at something else we can do with our inverting amplifier circuit. So here's our inverting amplifier, and we can develop a little bit of intuition about this. Basically, having the terminals here with one of them grounded means that the other one would have a potential of 0. So that's the magic that the op-amp is doing. And that means that the current that flows through here, so voltage VA down to ground, will have a certain current, and that exact same current must flow through the feedback path. So I1, these are the same currents because no current enters the op-amp, which means that the output voltage over here must be sufficiently far below the ground potential in order that this current I1 is the same as the input current. So this current here must be the same as the input. The only way that's possible is if the output voltage is sufficiently below the ground reference. So this is our inverting amplifier. And that kind of reasoning works out because we have the non-inverting terminal tied to ground. So you might say, well, what if we do something different, right? What if instead of tying that non-inverting terminal to ground, we instead hook up some other voltage there? So you could imagine actually using just plugging a voltage in directly, doing something like this, and that actually will create an amplifier circuit, which is interesting to analyze. But you can also consider using a resistor network. And if we use a resistor network, you might put a resistor here. If you use only one resistor, well, that actually won't make any difference because there's no current that flows into this terminal, right? So no current flows means no voltage drop across the resistor. So therefore, we actually need to use 2 resistors and form a voltage divider network. So with this circuit here, we now have a thing which is called a difference amplifier. So I'm going to run through the steps of analyzing this so that you can see how it works. So I'm going to name our resistors as A, B, C, D, so RA, RB, RC, and RD. And let's actually analyze this circuit. So remember our steps to follow. So we need to check negative feedback, and we can see that we clearly have that here in this circuit. We then need to assume equal voltages at the inputs. So let's call this Vn and Vp for the negative and positive terminals. So Vn equals Vp. And also assume no current flows into the terminals. So assume In equals 0 and IP is equal to 0. So those are the currents in here. So that's IN and IP. So those currents are 0. And then with that, we can solve the circuit. So we use, for instance, Nodal Analysis to analyze the rest of the circuit. So let's look at this one. We would like to know what is the voltage at one of our inputs. So for instance, Vp here, what's the voltage there? Well, we have a voltage divider network. So we can pretty much just write that one down straight away. So we have that the voltage Vp is input voltage Vb multiplied by the voltage over which it's measured. So with respect to ground, that's Rd over the total resistance Rc plus Rd. So that's just using a voltage divider formula for Vp. And then we also know that Vn is equal to Vp. So that's our same expression as before. That's Vb times this resistor combination. So we can then go in and write KCl at node Vn. And if we do that, I'll write this in terms of currents leaving, so my usual sign convention. So that is Vn minus Va divided by Ra plus Vn minus V out divided by Rb is equal to 0. And we can substitute what we know about Vn. So substitute for Vn, and here's what we're going to get. So our first factors, 1 over RA multiplied by Vn, which is this, RC plus RD, that minus VA over RA, plus, and we have a 1 over RB times Vn, VBRD over RC plus RD, minus VO over RB is equal to 0. All right, we want to simplify this and we want to solve for the output voltage. So to simplify, I can collect like terms. I notice that these two brackets here are equal, so I can actually bring those together, and I will have 1 over RA plus 1 over RB times VBRD over RC plus RD minus VA over RA is equal to V0 over RB. All right, getting a little bit closer. I'm going to solve for the output voltage, so multiply out by RB on both sides, and this is what I will get. I'm going to also swap the right-hand side over to the left-hand side. So this is V0 is equal to all of this, so 1 on RA plus 1 on RB times multiplying in my RB from the other side will give me RB RD divided by RC plus RD, and that's my coefficient of VB, minus it will be RB over RA, and that's my coefficient of VA, and that's all equal to V0. So I have here some coefficient which will result from the values of all of these resistors times VA, times VB, minus, again, some coefficient, which I can choose by choosing the resistors, times VA. So I have basically a difference in voltages, right? VB minus VA with some coefficients that I can actually choose by choosing my resistor sizes. So this thing's called a difference amplifier, but you might look at this coefficient here at the front of VB and think, oh, that's a little bit messy. Is there a combination of resistors for which this one is a little bit simpler? And one case that I would be interested in is if this entire coefficient here in front of VB was the same as the coefficient in front of VA. And in that case, I would get the actual difference between the voltages multiplied by some gain. So what if the coefficient in front of VB, so what if the coefficient of VB equals the coefficient of VA? What combination would actually give us that? So well, we can kind of write this down, right? The coefficient of VB is this, so 1 over RA plus 1 over RB times RB RD over RC plus RD. So that is the coefficient of the first term, and I want to say that that is equal to RB over RA. And I can simplify and solve this and say, well what condition must be true in order for this equality to hold? So the first thing that I'm going to do is clean up the first factor on the left-hand side here. So put that over a common denominator, and if I do that, then I will get RA plus RB divided by RA RB. So that's just multiplying each one by the denominator of the other, and then they'll have equal denominators and I can combine them. So that is then multiplied by RB RD divided by RC plus RD, and that equals my right-hand side. So I can immediately simplify RB is going to cancel here, And I can also cancel the RAs, so multiply both sides by RA, and that will cancel there. So let's rewrite this now slightly simplified equation. So I will have RA plus RB times RD divided by RC plus RD is equal to RB. So we're making a little bit of progress. I'm now going to multiply out this fraction, so just take that denominator and multiply it out to the other side. RA plus RB times RD is equal to RB times RC plus RD. And then looking at this, I can see that if I expand this, there's going to be some terms which will be the same. So I notice that here I have B times D, and also B times D over here. So if I was to expand these brackets, then those would be the same on both sides, and I could subtract them off. So this will leave me with RA RD is equal to RB times RC. And then it's kind of normal to write this in this format, so I'm just going to write it as a ratio. RA over RB is equal to RC over RD. So basically, if that is true, then our coefficients in front of our two voltages, so that was this coefficient and this one, then those two will be the same. So we can finalize where we're at. So basically, if that is true, if the ratio of resistors is that, then we have that the output voltage is going to be our simplified form that we wanted to select as RB over RA. So I'm just looking at here, we made these two coefficients the same, so I can choose the simple one. I'm going to choose the simple one at RB over RA. So it's going to be RB over RA, and it was VB minus VA. And so that then becomes the equation for our difference amplifier circuit. That we have simple voltage gain, and multiplied by, that gain is multiplied by the difference in voltages. And so this is a difference amplifier circuit, and is another sort of common pattern that you should know about and be able to analyze.